Okay, so the next section is called principal component analysis. It's the next part of linear algebra. We're going to do something useful with those eigenvalues and eigenvectors. So back to our case study here, foobartender.io. The data science team recently received a very terse text in SMS from the CEO. The text said, QA report, too long, didn't read, need top level only. The problem is that there was a quality assurance report. It looked over some data that came from a panel of judges that were scoring drinks mixed by our top bartenders. Now, there were 4 judges, and there were 15 observations, 4 measurements, 15 observations. One of the problems was that this was originally presented as a hypercube, a 4D illustration. CEO didn't like that too well. So let's go ahead and use principal component analysis to try to explain what are just the top-level, most important details. Again, what if you had not just 4 dimensions, but maybe 4,000 dimensions? How could you really get in and start to look at the structure of this data in a way that makes sense for decision makers? Or for anybody, actually. So I've got some raw data here. I've got 4 judges are scoring drinks mixed by the top bartenders. And so we've got Judge 1, Judge 2, Judge 3, Judge 4. And then over here you've got a column describing the different bartenders, Carol, DePauli, and Kirill. Okay, we're going to use principal component analysis, usually call that PCA. And this will help reveal the internal structure of a data set. I kind of feel like we're on some sort of archaeology expedition here. In other words, it's a way of saying, how can we best explain the variance that's in the data? In many cases, you're going to have far too many input variables to make sense of. So PCA provides an overview, if you will, of the most important learnings. You can visualize this if we're talking about multivariate data. Again, a lot of different variables. Suppose we have a set of coordinates in an n-dimensional space, some high-dimensional space, and we've got 1 axis for every variable. Okay, so let's build that up. If you had 2 variables, you've got a 2D flat diagram. If you've got 3 variables, you've got 3D, some volume, 4D, 5D, 5000D, etc. It gets very complex. What PCA provides is a low-dimensional view of your data, a projection of it, a shadow of it, if you will, of what the real structure is inside. And it really, you can think of considering that projection from the most informative point of view. So how can you get the camera angle right is a good way to put it. Okay, so the big idea here is that to use only the first few principal components, and those are eigenvectors, out of the covariance matrix. Just peel off the most important ones so that the dimensionality of the data is reduced. We could take it from 4,000 variables and just consider the top 2 or 3. Not top 2 or 3 variables, but rather top 2 or 3 eigenvectors of those variables. So this is an issue that we grapple with continually in machine learning. It's typically called dimensional reduction. The approach to this is sometimes called low-dimensional embedding. You'll hear that. If you read papers off of, say, Netflix Prize, they talked a lot about low-dimensional embedding. In other words, PCA helps us to simplify data by transforming it down to a smaller coordinate system. So we can go from 5,000D data down to 3D data, something we can visualize. In terms of computational thinking, there's a kind of pattern generalization here. We can basically take and tune the number of dimensions from our input variable space, adjust it down to where we can actually view the structure in the data. So when we tune the dimensionality, if you will, a less granular structure implies more generalization. And that really is, in a nutshell, machine learning. Being able to generalize from a lot of data into fairly consistent patterns that you can use to predict events in the future, that's machine learning. On the other hand, getting a more granular structure implies capturing more variance, more nuances. So that might be, for instance, if you wanted to improve how you're doing customer segmentation, you adjust the granularity up. So essentially, tune the number of dimensions. Okay, so consider that we're modeling thousands of variables, thousands of x's. That can be a problem. And it may just even be a performance problem. It may be that your models have a cost of, I don't know, n squared. You don't want thousands of input variables. But you could use PCA to transform your raw data down into something much more manageable. Maybe go from thousands down to 20. And really, that's what people are doing when they're using something like k-means clustering. PCA is good for analyzing data. Clustering is good for cases where you have really enormous amounts of data and you want to calculate it in a very efficient way. But they are related. OK, so we've got 4 variables in the data set. And again, we don't want to show our CEO a 4D visualization. So we're going to simplify that down to the most important 2 dimensions instead. So we've got some Python here. And there's a function here defined as printcomp. This came out of the Glowing Python blog. Really great examples there. I've got some Python here based on NumPy, which implements a principal component analysis. There's other ways to do this in Python. You could use scikit-learn. There's a few different kinds. But I'm going to define my function here. Cut and paste this. OK. So what happens is I take input matrix A, and I'm going to process it a little bit. I'm going to take and subtract off the mean, the transpose, et cetera. Just get it in a more regular shape. So that's going to be matrix M at that point after it's transformed. But from there, I'm going to find out the covariance in that matrix and then find the eigenvalues and eigenvectors of the covariance matrix. And I'll save those off as a couple of variables, latent and coefficient. And then I'm going to take and use that. I'm going to take the raw data, or rather the massaged data. I'm going to apply the eigenvectors. So I can take my large high-dimensional space, transform it down to a small low-dimensional space. So let's take the judges' scores for our bartenders, matrix A there. I'll show what A looks like. OK, and then I'll run principal component analysis. OK, and then if I print out what these different values are, coefficient there, and then latent there. So coefficient was my eigenvectors. That's how I transformed down to a smaller space. Eigenvalues are in latent. We'll show those in a bit, but you can see that they're decreasing in value. And that's very important. That actually helps explain how much variance we've reduced by peeling off an eigenvector off the covariance matrix. And then the last one is score. And so this is actually taking those eigenvectors and applying it to the raw data to transform it down. OK, now I'm going to do a little trick here in Python. I'm going to take and analyze this for what is the proportion of variance that each of those eigenvalues has explained. So if I print this out, great. OK, this is a fancy way of basically taking the sum of the eigenvalues and dividing each one cumulatively. What it tells me is that the first eigenvalue explains approximately 95% of the variance in all of the data. The second eigenvalue explains 0.04%. The third one explains 0.01. The fourth one explains, well, really not very much. You get diminishing results. But the idea is that by the time you've gotten out to your second principal component, you've already explained like 98% of the variance. Almost all of what's going on in terms of the structure of the raw data has been explained off of just 2 dimensions. That's what we're trying to do. So this shows it here in terms of a table. Probably a little bit easier to read it in this format. But we've got these different principal components that we're peeling off of our covariance matrix. The first one is explaining, like I say, 95%. And then cumulatively, the first one and the first 2 together explain 98.58%. The first 3 explain 99.67%. And the fourth one, of course, explains all of it. What that means is that we can use the first 2 principal components as a way of visualizing this data in 2D. And get almost 99% of the variance. That's pretty good. So we're going to do that here. Basically, foobartender.io data science team has used Principal Component now to take this large visualization in 4D, transform it down into 2D, something that's very consumable. And so you can see here, if I take all the data points of the different bartenders and they're color-coded, I've got component 1 on the X and component component 2 on the Y. And Kirill is shown here in light green, DePauli in red, and Carol in black. You can see how they kind of cluster. And so this is a way of telling where are the scores relatively for each of these different top bartenders. And really, this is a way of clustering. You can kind of see that, well, all the Carol scores are clustered over there, and all the Kirill scores are, yeah, they're dispersed over here. DePauli is kind of in the middle. You start to get the idea that, yeah, Carol's doing pretty well.